All right, let's talk about decoders, right? A form of combinational circuit. And when we ask what a decoder is, it's a multiple input, multiple output logic circuit. It's going to change input codes into coded outputs. Right? Both the inputs and the outputs are dissimilar, meaning you won't get the same output as you got for the input, right? Because we're usually decoding something that's been encoded in a special way. So this is an n to, actually, that should be 2 to the n power decoder. Right? That's one type. There's binary coded decimal decoders we'll take a look at later in the course. All right, for now, we're just going to do n to 2 to the n. And we use it in lots of applications. Data multiplexing is an area where this is decoded. We've seen muxes. We haven't talked about demuxes yet. Memory address decoding. This picture here can represent how we would then change something that's coming in as an input to where it's stored in memory. We'll take a look at that later in the course with registers and memory addressing. That's a more advanced topic that we're not to. And 7-segment display. Right? If we've not seen these yet at this point in lecture, a 7-segment display is a set of 7 LEDs. Right? They're individual lights that you can turn on or off to create a pattern. In this case, both of these segments are turned on, so it creates the next symbol 1. Right? So we'll take a look at those at some point in the course. So decoders are used in a lot of places. Right? A general symbol for a decoder will have the inputs over here on the left. Like I said, we can have n inputs, 2 to the n outputs on the right, and it's a maximum of 2 to the n. You don't always have to generate all of the 2 to the n outputs. We'll take a look at that later. Today, we'll just be generating all of the 2 to the n outputs. And these 2 to the n outputs are unique, right? None of these outputs will be the same. It's a little bit different than what we've seen in a truth table before. Let's start with the most simple decoder, a 1 input to 2 output decoder. Right? N equals 1 input lines, a maximum of 2 to the 1, 2 unique output lines. Our truth table would look like this. Our input we're calling A. Our output lines we're going to call D. And we'll have output D0 and D1 because we need 2 outputs. Right? We need to generate a unique output. And what this circuit basically does is it tells you, it activates the output line. So this is an active high decoder, meaning our output will be high to indicate what our input value is. So our input value A is a 0, meaning line D0 should be a 1, and every other output line should be a 0 whenever our input's a 0. Whenever our input's a 1, then output line D0 is a 0, output line D1 is a 1. But basically, the output lines are telling you what was the value of your input, right? They're decoding the input values. And now, if we wanted to solve, right, for D0, we want to write an equation for D0. Well, D0 is equal to A naught. And so here's D0, here's A naught. And here, D1 happens to follow the pattern of A, so we could just say D1 is whatever's sitting there on A in this simple circuit. Our next circuit is a 2 input to 4 output decoder, often referred to as a 2 to 4 decoder. People usually don't use the words input and output. They understand that when they say 2 to 4 decoder, 2 on the left is the number of inputs, 4 on the right is the number of outputs. Again, this is going to be an active high decoder. Right? We're going to convert then the binary information from 2 input lines. So our 2 input lines we're going to label A1 and A0 to a maximum of 2 to the 2, 4 unique output lines. So again, unique outputs means we're only going to have a 1 then in a unique position in each one of these outputs. So I've shown the ones here in red. Remember I said these outputs tell you what the value of the input was. So the way this circuit works is whenever our input is a 0, well, the binary 0, 0 stands for a decimal 0. So line D0 will be a 1. All of the other output lines will be zeros to tell us then, right, D0 is uniquely a 1, all of the others are zeros, to tell us that the input was a value of 0. When our input is 0, 1, binary 0, 1 is decimal 1, well, line D1 will be a 1, all of the other outputs will be zeros. When we have this binary combination of 1, 0, which is a decimal 2, we can see that D2 will be a 1, will be active. All of the others will be zeros or lows. When our input is a binary 1, 1, which is a decimal 3, line D3 is active, is a high, and all of the others are zeros. It makes the equations very simple to write because when we solve for D0, well, only in one place is it ever a 1. So we can say D0 is a function of A1 not and with A0 not. D1 is only a 1 here when A1 is a 0 and A0 is a 1. So A1 not A0. D2 is equal to A1 and with A0 not, or minterm 2. This is minterm 3. We'll see later that an active high decoder is known as a minterm generator. And so if, based on these equations, if we were to draw the circuits with the AND and the NOT gates, our circuit looks like this, right? We've got A0, A1 here. Here are our 4 output lines. Simple circuit, right? Let's then take a look at what this is in Verilog. And actually, let me just pop up Quartus. I think we'll write this together, right? I've got an example written out here, but let's sit down and write this because we haven't done much in the way of behavioral Verilog. We did take a look at in our MUX lecture, we saw that when we wrote a MUX using a case statement, it generated something called a decoder, and we didn't really know what a decoder was yet. Let me just, like I said, pop up Quartus and let's write this circuit together. All right. So I'm going to get a new Verilog file. And how big is that font? Let me make the font big. Let's maybe make it 20. And I'm just going to say, this is an active high 2 input to 4 output decoder. All right, so we start with our keyword module. I'll call it decoder 24. AH maybe for active high. And we said our input, well, we're going to have 2 inputs, A1 and A0. So I'm going to say input wire, 1 down to 0. So remember, when we have size, when something's more than 1 bit, we specify the size when we declare the signal out to the left, A, and output wire. We have 4 of those, so 3 down to 0 gives us 4 bits, D. Right. And module. We could write the bitwise equations. You've seen how to do that before, but we want to start working on behavioral, or what's also known as procedural Verilog. That means we write something with an always statement. And we're going to write this in the form of a case statement because a case statement actually generates a decoder. So the always block, we need to say always at, and in here in this sensitivity list, we have to say, what is the output sensitive to? Well, the output is sensitive to any changes on the input A. I'm going to begin the block with the begin keyword. I'm going to end the block here. And our code then will go between begin and end. So with a case statement, I can say case, and what we want to evaluate is the value of A. Right? Because A is driving our truth table output. And so what we say here is now on the left, we're going to specify what A is. And I'm going to say when A is a 2-bit, so the 2 in the apostrophe says the number of bits. B says binary. It says whatever number I write after this is going to be a binary value. I could write just a 0 and it would fill the left with all zeros, but I'm going to write out the pattern. When A is a 2-bit binary 0, colon. In that case, I want my output D to be a 4-bit, because D is 4 bits wide, a 4-bit binary 0, 0. No, sorry. We said that 0, 0, 0, 1, because D0, this is D3, D2, D1, D0. So D0 needs to be a 1. All of the other lines need to be a 0. Okay. Now, D is a wire type. Inside a procedural block, so a procedural block for us starts with an always statement. The signal name, or the signal type on the left-hand side of an assignment operator, this is an assignment operator. This signal type can't be a wire type, it has to be a reg type. That means we need to declare a reg in here. I often just put the letter R in front of mine, so I'm going to say reg RD. Sorry, it needs to be the same size as D. Reg RD, I'm going to declare that signal. So here, I need to make this a reg. So RD, I want to assign to RD. Right. And I'm going to go ahead and fill in the rest of the table. So the case statement, when this is a 2-bit binary, 1, RD is going to be equal to a 4-bit binary 0, 0, 1, 0. Simply because the pattern here is D3, D2, D1, D0. Might have been better if I'd have written the truth table in that form. D3, D2, D1, D0. Right. So when we put a 1 here, we're saying that that D0 bit is equal to a 1. Right. When we put a 1 here, we're saying the D1 bit is equal to a 1. Right. And basically with a case statement, we're writing the truth table. We don't have to develop any Boolean equations. Right. When our input's a 2-bit binary 1, 0 or 2, RD, what we want to assign to RD is a 4-bit binary 0, 1, 0, 0. Right. That unique pattern. Finally, when it's a 2-bit binary 1, 1, RD will assign to that a 4-bit binary 1, 0, 0, 0. And then we have to have an end case statement, right, as part of the syntax. The last thing we have to do is we have to assign the reg to the wire because we've not connected anything to the output yet. And we can do that before the always block, after the always block. We use a continuous assignment statement for that. We assign to D the value of RD. And we call this a continuous assignment statement. The signal that's on the left-hand side of this assignment operator must be a wire type. On the right-hand side, this could be a reg, a wire, a constant. Same way here. Here on the right-hand side, these types can be wire, reges, numeric constants. Left-hand side inside a procedural block, inside an always block, has to be a reg type. All right, let's save this. I might already have a file with the same name. We'll just write over it. But remember with Quartus, you have to save file with the same name. Right. And let me remove some of the other block diagrams from this project. And let's just have our decoder in, set it as a top level entity. Let's run an analysis and synthesis to see if I made any syntax errors. And if not, we will then run a simulation after that. If I made errors, we will correct them. All right, so no syntax errors. So let's create a simulation, file new. All right, university program vector waveform. We're going to set, sorry, I'm going to set the end time here. 20 nanoseconds will be enough. Let's import our signals. All right, and let's specify A. So my least significant bit, I'm going to overwrite the clock and use the 10 nanoseconds. So I'm going to double the period at 20 nanoseconds. We're going to save this. And let's try to run the functional simulation now. All right. So let's look at this. All right. Let's look at our lines. So when A0 is a 0, A1 is a 0. So it would help if I popped up the truth table again for a second. All right. So remember, when our binary inputs are 0, 0, we should uniquely have D0 as a 1. When we have a 1, D1 is a 1, and so on. I'm going to close this. This is why I don't like to look at the individual ones. I like to say here, when our input is a 0, right, binary 0, 0, decimal 0, our output is 0, 0, 1, where we can see that line D0 is a 1, every other line is a 0. When our input here is a 1, binary 0, 1, line D1 is a 1, every other line is a 0. When our input is a decimal 2, binary 1, 0, we can see that line D2 is a 1, every other output line is a 0. Finally, when our input, right, is a decimal 3, binary 1, 1, line D3 is a 1, every other line is a 0. So the circuit is behaving as we specified in the truth table. And that's the way an active high 2 to 4 decoder works, right, with the case statement. Like I said, as class goes along, we're going to be writing more of this behavioral code. That's why I want to practice this. All right. What we'll see is if we go out to Tools, Netlist Viewers, RTL Viewer, see the circuit it generated. Well, it shows us it generated a decoder, which is good. That's what we were trying to generate. Right? Remember, we said for behavioral Verilog, whenever we use case statements, it tends to generate a decoder. All right, so that's our 2 to 4 decoder. That's the same Verilog here in your example. Right. Now, we could also add an enable to this. Right. So if we go back, then we had this truth table. What we want to do is we want to add on to that. We want to add an enable input. And we're going to say this is an active high enable. So remember, active high enable means whenever the enable is a 1, what's ever sitting on the input can flow through to the output. Whenever enable is a 0, right, for active high, a 0 disables it. We don't care what's on the input. And what we're going to specify is that the output should be all zeros. So on our decoder, the output should be all zeros when the circuit's disabled. Which makes sense because the way the decoder works is that a 1 tells us what the input is. So if everything's a 0, right, none of these lines uniquely have a 1, so our circuit's disabled. So we wanted to pick that then as a disabled behavior. All right. So here's our truth table, right? We could go ahead and, well, if we were to solve this, we would say then whenever this is a 1, we're going to use an AND gate. Right? So if you look at everything except the enable signal, this is the same circuit as we had before for our 2 decoder. We had, right, when A0 not is ANDed with A1 not, line D0 should be a 1. Well, we simply AND in the enabled, simply because this is an active high. We took a look before. We said when we have an active high enable, we've got this AND relationship, right? And that will enable the circuit whenever this is a 0. It would drive the circuit to a 0. That's why we're able to use that AND gate. I said you could go back and you could derive the Boolean equations for this and you would get the same equation, right? Which is a good exercise for you to do. But this ends up being our circuit. We simply then add this enable as a third input to our AND gate. And what we want to do then is we want to take a look at how would we write the Verilog with the enable. So let me copy this. Let's write a new Verilog file. We're going to say active high enable. when enable is a 1, A flows, input A flows through to output, right? When enable is a 0, output is all zeros. That's the behavior we want. So I'm going to call this active high en, enable. I'm going to pull these out of here. Didn't have to, but when I start getting a lot of signals in the port list, I prefer to do it this way. And we're going to have this en signal, A and D. Doesn't matter the order we list them in. Enable is a single bit, so I'm going to put it on its own line, input wire, en. Right. All of this behavior stays the same, right? We want the input A to flow through to the output whenever this is enabled. So we're going to add an if statement. We're going to say if en, so if that signal is equal. So 2 equal signs is the relational comparator equals, right? So if enable is equal to a 1-bit binary 1, I'm going to surround, then I'm going to say where the if statement begins, where it ends, else then RD is equal to a 4-bit binary 000. Right, so what we said here is if enable is equal to a 1, then go ahead and run our usual decoder input through to the output, what we'd specified before the way the decoder worked, but we said otherwise when enable is a 0, we want our outputs to be a 0. And so here we're testing the condition. If this is true, this code will execute. But if this test condition is false, that's what else says. Else says if this was false up here, right, go ahead and run this code, right, which then says put the output 0 on all of our decoder lines. So these are mutually exclusive. If this is true, do the following, else do this. So when this is true, it will perform these actions, it will not perform this action. But when this is false, it will execute the else branch. So this is a if true, do this, else do that. So mutually exclusive conditions. Now begin and end. If you have a single line, you don't have to have begin and end. So I could put begin, end here, but you can see that it starts getting a little tedious when you have single lines or single blocks of code. So let's just go ahead, let's see, let's save this. Let's remove this one from the project. All right. Let's create that as the top level. Let's run an analysis and synthesis on this. Sometimes then people start, well, we indent this to make things easier to read. We indent this to say, okay, this block of code belongs to this if statement. This block of code belongs to this else statement. It usually just makes things easier to read. Right, as you can see, the syntax was just fine. What I'd like to show you as well is when you have a single statement, you do not have to have the begin and end blocks, so I tend not to use these. And also, it will think of the case statement as being a single statement as well, since it has a beginning to the case and an end to the case. So I should be able to save this, run analysis and synthesis again, and not get a compilation error. I did not get a compilation error, which is good, and we can then create a new simulation. I always forget to set the end time first. You'd think I would learn. 40 nanoseconds. Let's import everything. All right. I want to go ahead and throw my able signal at the top. All right. So this is going to be 10 nanoseconds. This I'm going to double to 20. Enable I'm going to set at 40, so it'll be low for half and high for half. I'm going to save this with the default name suggested because we know Quartus likes that. I'm going to run the functional simulation. All right, so what we want to see now here, right? Whenever the enable signal is a low, our output should be all zeros. So enable's a low from here to here, the output D is all zeros. Let's take a look now. When enable's a 1, we should see what we specified before on the truth table, right? When our input's a 0, line D0 should be a 1. Just open this up to confirm this is D0. All of the others then are zeros. Right, when our input's a 1, line D1 is a 1, the others are zeros. When our input's a 2, line D2 is a 1, the others are zeros. When our input's a 3, line D3 is a 1. Right? So this shows that our circuit is functioning as expected, right? And this is what then the Verilog looks like with an enable. We just pop this back up. Like I said, we want to write these case statements. We want to get away from the bitwise behavior. You have an example here in the lecture notes of the same circuit as well. This is we just wrote and simulated. All right, so now as you might suspect, if we can make 2 to 4 decoders, well, what if we have a 3-input decoder? So what we call a 3 to 8 decoder is a 3 input to 8 output, so 2 cubed, right, is 8, 3 inputs, 8 outputs. It's going to be active high. That means only one bit is uniquely high for each input. This is in general what the symbol for the decoder looks like. We could show the 3 lines, A2, A1, A0, and the 8 unique output lines. Here is our truth table. Our inputs here on the left, A2 is our most significant bit. I'm showing then, I'm going here in the reverse order, D7 down to D0. Well, again, when our input is all zeros, D0 will be a 1. All of the other outputs are zeros. When our input is 001, decimal 1, D1 is an output. When the input is 2, so there's the binary pattern for decimal 2. When the input is 2, D2 is a 1. Everything else is zeros. When the input is a 3, 011, binary for decimal 3, D3. Similarly now, input is a 4, a 100, D4 is a 1. D5 is a 1 when the input's a 5. D6 is a 1 when the input's a 6. D7 is a 1 when the input is a 7. Right? All the other lines are 0. So we have just in one place, we have this unique 1. Right? So that's what that active high decoder is telling us. It's telling us then whichever line's high tells us what the decimal value of the input is. Right? So it's decoding binary to decimal in a way. Right? All right, so there's our truth table. Right? Now we've been structurally building some other circuits. So one thing we might want to ask ourselves is, can we build a 3 to 8 decoder using 2 to 4 decoders? Right? How many 2 to 4 decoders will we need to build that? Well, we need 2, right? We need at least 2. And the reason I say we need 2 is we look at the number of outputs we need. This says we need 8 outputs. Well, a 2 to 4 decoder, well, only one of them has 4 outputs. So we need 2 to get a total of 8 outputs. So here I've used the symbol for a 2 to 4 decoder where we have the two input lines and 4 output lines. So we could go ahead and tie D0, D1, D2, D3 to this decoder, and then D4, D5, D6, D7 to this decoder, right? And I went ahead and said, okay, well, maybe I can wire A0 and A1 to this decoder. And that's going to show me then what's on that. But then what do I do with A2? Because I've only got 3 input lines, but when we use 2 of these decoders, we've got 4 inputs. What do we do? right? Because if I were to wire A2 to either one of these lines or both of these lines, they'd both be generating outputs, right? It's almost like I wish I had a way to turn one of these on or off at a time, because we need to uniquely only have one of these lines in each of these decoders to generate a 1, right? If D0 here is generating 1, I don't want the D0 here to be generating a 1. Not if my input is all zeros. Right? When my input's all zeros, I expect this D0 to be a 1, all of these other lines to be zeros. When my input is a binary, is a 0, 0, 1, well, I would expect this line to generate a 1, everything else to generate all zeros. Let's take a look at that truth table again. Right? So I've color-coded it a bit. And I said over here, let's look at D3 to D0. If you look at this pattern, this is the pattern for a 2 to 4 decoder, right? This is the output pattern. And we know that a 2 to 4 decoder could be driven by these two inputs, A1 and A0. Here in the green, right, D7 to D4 in this portion, it also looks like a 2 to 4 decoder, right? We have a unique set of 1s. Everywhere else we have zeros here. Same way up here, everywhere to the left we have zeros. So this looks like a 2 to 4 decoder. And this, then we know that this would drive a 2 to 4 decoder, A1 and A0. So we need to figure out, what do we do with the control lines A2? Well, notice here, when A2 is all zeros, if we could get this extra 2 to 4 decoder to generate all zeros, and if when A2 is a 1, we could get this to generate zeros. Basically, when A to 2 is a 0, we want to disable decoder. If we call this decoder 0 and this decoder 1, we want to disable decoder 1. When A2 is a 1, we want to disable decoder 0 and enable decoder 1. That's what I'm telling you down here, right? When A2 is equal to 0, inputs D3 to D0 are the same as a 2 to 4 decoder. When A2 is equal to 1, outputs D4 to D7 are the same as a 2 to 4 decoder. So that suggests, right, we can build a 3 to 8 decoder from this, but we need to be able to turn one decoder on or off. What if we were to treat this like in 2 to 4 decoder with an enable? Because when I tried to use the 2 to 4 decoder, I was not using one with an enable, was I? I did not place one with an enable on here. That's why we want a 2 to 4 decoder with an enable. We want to be able to enable and disable it. Right? And so we could say here, right, what we just described is when our input A2 is a 0, we want to enable decoder D0 and disable. We want the enable signal to turn off, right? Decoder 1. When A2 is a 1, we want to enable, so the 1 will enable this, the 0 will disable this. That's the behavior that we want. So enabling decoder 0, so enabling decoder 0, right, because this happens to be a 1, we'd say not A2 if we were to solve for this, right? This is an output. Here, this one that we have in the output would simply be A2. So we say enable decoder 1 equals A2, enable decoder D0, this output is equal to not A. And so when we lay down these decoders, right, as we define them as this one, if we define as D0, we put the enable signal, we connect A2 to the enable. We said A2, then the equation was not A2 to the D0. We said the equation to the D1 decoder was simply A2. And now we tie our outputs D0, D1, D2, D3 to decoder D0, D4 through D7 to decoder D1, and we build a 3 to 8 decoder from 2 to 4 decoders. We need that enable to do it. Right. There might be some ways to do it with external circuitry without the enable, but here it's just easier to actually use the enable. All right. So that's how we build a 2 to 4 decoder using That's how we build a 3 to 8 decoder using 2 to 4 decoders. Similarly, we could just straight up build a 3 to 8 decoder with its own enable. Right, we don't have to build it using 2 to 4 decoders. We could just write one, especially now that we have Verilog. It's easy to define a circuit. Right. And so we could just simply go back to the 3 to 8 decoder truth table that we started with. We could add an enable, so we add a fourth input to that, right? And then we specify then what we want the behavior to be. Right, we're going to then say when enables is 0, right, again, which decoder do we want to turn on or off? Which set of lines? In this case, right, we want to enable decoder 1 whenever the enable and A2 is a 1. Here, we want to enable decoder D0, that upper half when enable is a 1 and A2 is a 0. Right? So even though we aren't using 2 to 4 decoders, right, if we go back to this truth table, we're going to add an enable to it. And what we want to say is we want the whole thing to be disabled to produce all zeros. Right? Whenever enables a 0, right, we want to enable then this portion in conjunction with A2. And then we want to enable this portion in conjunction with A2, this portion here, when A2 is a 1. Right? That's what this truth table is saying. Right. And when we do that, again, we're building this from 2 to 4 decoders. Right. We then generate this signal. This is a slightly different approach than here, where we use the 2 to 4 decoder. Right. With the enable, we used A2. What we did here is we said we wanted to add one more signal here. So besides A2, we wanted to add an additional signal to the 3 to 8 decoder. That's what we did here with enable. So we still have A2, A1, A0. We've got the enable. Right. So we have 4 inputs. If we were to draw out then the truth table, the full Boolean truth table, you could do that. Right. You'd have 16 unique inputs. You could generate the equations. But what you'll find is that you come up with the same set of equations. We can go on to build larger decoders as well, right? We could build 4 to 16 from 3 to 8s or from 2 to 4s. Right? This is an example of how to do that with a 3 to 8 with a decoder. But you get the general idea. What we want to do more in this course is describe things with Verilog. We want to learn how to use these circuits. Right? We've seen why an enable is important in some of the circuitry, because what we want to do is we do want to sometimes be able to enable or disable the circuit. And what we'll do in the next lecture then is we will see how to use these decoders as min-term and max-term generators.